What's up, team? Let's talk about similar figures. So, on the board here, similar figures can be thought of as the result of a dilation. If you don't remember what a dilation was, go check that video out or check those notes out. That's important. Generally, it's a transformation that makes something go bigger or smaller in size. So if we think of similar figures as the result of a dilation, that's going to give you a head start on how most people think about similar figures. So I have two things here. I have this rectangle A, B, C, D, and then this bigger rectangle A prime, B prime, C prime, D prime. And the A prime, B prime, C prime, D prime is just a result of a translation from the original A, B, C, D by a scale factor of 2. All that means is it doubled in size, and we can see that pretty clearly. AB has a length of 3, whereas A prime, B prime has a length of 6. 3 times 2 is 6. B prime, C prime is 4. Over here it's 2, so it doubled in size. 2 times 2 is 4, and we can keep going, and that pattern holds. So if this thing has a scale factor of 2, that just means everything doubles in size. Both the corresponding side lengths double. The perimeter, if you add all 4 sides up, it doubles on the next one. So if that's the case, if you can show that two figures, one is just a dilation of the other, then you say you have similar figures. So we can write a little statement up. So A, B, C, D, that's this rectangle here, is similar to, that's just a single squiggly line without the equal signs underneath. Equal sign underneath means it's congruent. This is not that because they're not congruent. They're just the same shape but different sizes. So we say it's congruent to A prime, B prime, C prime, D prime. So again, A, B, C, D, similar to A prime, B prime, C prime, D prime. And that means the exact same shape with different sizes. Okay, when working with similar figures, there's some really neat relationships that we can kind of uncover. So neat relationships. Number 1, something that I think is really cool. If you just look at this figure, A, B, C, D, and we take AB, and we set it up as a fraction over BC. So the length of AB, you can see, is 3, and the length of BC, you can see, is 2. So AB divided by BC is 3/2. Oh, okay, cool. Like that's not so neat yet. But if we look at the other figure, and we take A prime, B prime, which is the corresponding side to AB, and then B prime, C prime, B prime, C prime, well, we get 6/4. Which of course can be reduced to 3/2. So when you're looking at corresponding sides of similar figures, in this case we get 3/2, over here we get 6/4, which reduces to 3/2. That ratio is going to be the same. So we say that similar figures, the corresponding sides are always proportional. So the 3/2 equals 3/2. So we're going to use this fact to solve problems in a little bit. Neat relationship number 2. This stuff works kind of across figures as well. So not only are corresponding sides proportional within the given figure, but you can kind of cross paths here a little bit. So here's what I mean by that. If we were to look at A prime, B prime, and compare it to AB, well, that makes sense. They're corresponding sides. So we'll have 6/3, which of course is 2. All right, and that kind of makes sense. Scale factor of 2. Let's look at the other one. B prime, C prime. B prime, C prime over BC. And that's 4/2, which of course is also 2. The ratios are the same. They're proportional. Again, this one stems from the fact that one's just a dilation of the other one by a scale factor of 2. So it's doubling in size all the way around. The only thing about these neat relationships that can get people in trouble is when they mix things up. So for example, if we did AB over BC, and we're like, oh, that must be the same thing as B prime C prime over A prime B prime. Well, that doesn't work because you flipped it inadvertently. Or like down here, because we have the primes on top and the originals on the bottom, prime on top, original on the bottom. If you were to flip one, then you'd end up with 2 = 1/2, and that's just not true. So you have to be consistent as you work with these relationships. Let me do a couple examples. Hopefully that'll make things a little bit more clear for us. All right, a couple examples to tackle. I changed the values over here for ABC and our A prime, B prime, C prime, D prime. Now, the length of AB is 15, the length of AD is 10, and we don't know the other stuff, but we know it's a rectangle, and we know that these two figures are similar. Over here, a prime b prime is x. That's our unknown. That's what we're going to try to solve. And then our a prime d prime is 30. So leaning on our the neat relationships that we looked at just a moment ago, a couple different ways we can approach this. We can do AB over AD. AB over AD has the same value as A prime B prime over A prime D prime. Okay, well, let's put it in numbers. Let's make this stuff make sense. AB is 15. AD is 10. And then over here, A prime B prime is X. And A prime D prime, as in dog, is 30. Okay, now we have an equation with just a single variable. We can solve this business. Now, remember when solving equations that are in the form of fractions, we can cross multiply, but here's why that works. Basically, what we're going to do is multiply both sides by 10 to dump this fraction over here. So multiply by 10, those cancel, multiply by 10 over here, and then we learn that 15 equals 10 times x over 30. Now what we're going to do, a couple different ways. We can do some reducing before we multiply. I'm just going to get my multiply on. I'm going to multiply this side by 30. Those cancel. Multiply this side by 30. Now, I'm realizing I need my calculator. So 30 times 15, opening up my calculator, 30 times 15 is 450. So I learned that 450 equals 10x. Divide both sides by 10, x equals 45. Okay, so what's that mean? That means the length right here is 45. Nice. Another way we could have looked at this one, I'm not going to show all the algebra for this one, but we could say that AD over A prime D prime, or whatever that scale factor is, hopefully you see pretty quickly it's 3, because 10 times 3 is 30. Well, we could have just taken this and multiplied it by 3 as well to get 45. 15 times 3 is 45. So both these relationships work. They're both going to take you to the same place. In this case, we got 45 for both of them. Next example, two triangles. Triangle cat is similar to triangle dog. I should have these triangle symbols in here. A couple different ways we can do this one, similar to the last one. We can try to match these ratios up. So that's the way I'd like to do it. I'm going to look at CA over DO. And I know those are corresponding sides because they're the first two letters of each expression. DO is 14. So CA is 7 over 14. Oh, nice. That's a ratio of 1/2. That's helpful. It's a nice simple one for us. And then AT over, let's see, OG. OG is going to be 11 over X. Well, we know that these two have the same ratio. That's the neat relationship that we discussed. So we can kind of combine these two ideas and say that 1/2 equals 11 over X. Multiply both sides by X. We learn that X equals 22. Another way we can look at it is, 1 over 2. 2 is twice as big, and 22 is twice as big as 11. So this distance right here is 22. And we can do the same sort of thing to find Y. We know that DG is going to have the same ratio here with CT. And then we just learned there's a scale factor of 2 going on. Because when you double 7, you get 14. When you double 11, you get 22. So when you double Y, you get 24. Well, half of 24 is 12. So a couple different ways you can approach this. Lean on those neat relationships. Just remember scale factors. Similar figures are scale factors of one another. If you have a pair of corresponding sides, if you have both of those pieces, then you can find any of the pieces. Okay, let's dive into some practice problems. Let me know if you have questions. You got this.